Today I'm going to cover sections 5.3 and 5.4, equations of equilibrium and 2 and 3/4 members. Okay, so we have seen this before. We have, in order for, this is a two-dimensional system, in order for the system to be in equilibrium, all three of these equations have to be satisfied. Okay, so summation of the forces in the x direction, summation of the forces in the y direction, and the moments about any point are all have to be equal to zero. Okay. And one of the things they say is always about any arbitrary point. So this has to be about really any point on the in the object. It cannot have a moment. Okay. Uh, okay. Okay. So one of the things we're going to notice when we take a look at a structure, or one of the things we should recognize, is that we can often simplify the analysis of a particular system by considering certain types of members. If they have an object or a part of a system has just two forces acting on it, we can make a simplification. Now here are three possibilities. You could have forces acting in this. You have a force acting at B and a force acting at A, and or off in some direction, and here's another one, and they're off in some other direction. And one of the things you note here is that if you have forces that are acting, let's say, in these directions, and they don't necessarily, in this case, they could, if you drew the lines of action, you might have a point where they cross over. But if you have a system like this and you were to look at any point along this, what you would find is that these would develop a moment. So this is not necessarily an equilibrium condition, and nor is this. Okay. So for systems in equilibrium, what you're going to find is that the forces that are acting are going to be equal in opposite direction. And the line of action, you can draw a line that's going straight through um, both of the forces. Okay, so they're going to be equal opposite direction, and they have the same line of action, right? And this is going to be an important point when we start to look at structures. So when we're taking a look at truss structures, okay, in the next chapter. But we can use this idea for simplification here. Okay. So for equilibrium, this is really what we have. So this is really all we're going to be thinking about in terms of this particular chapter. For an equilibrium condition, we have this. And in fact, if it wasn't the case, then the system would not be in equilibrium. Okay, and that is, there are cases where that can happen, right? Where it's not in equilibrium. And so when it's not statically and not in equilibrium, what we would consider this to be that it would be considered to have improper supports. Okay, so only in special cases. So if it's not in equilibrium, or the that actually portion of the object would be considered to be improperly supported. Okay, so here's an example. Connection points, and this is I don't know what this is. Maybe this is some kind of jack. This is just like a backhoe. And you would find that from point you have just two connected to 2 points, the forces would be equal and opposite whatever force is acting on these. And the same thing here along the line of the piston. Okay. So what we will find is this is the case when it's in equilibrium. They're on the same line of action. Okay. So just the steps for solving the 2D equilibrium problems. Okay. If you're not given, you'll establish a XY coordinate system. Okay. The next thing is to draw the free body diagram, then apply those equations of equilibrium. Okay. Now, a key part of this, of course, is that your free body diagram has to have all the forces that are involved in the object, all of them external forces acting on the object. Okay. Okay. Just um, a few points, right? If there are other cases where you have so-called redundant supports or it's an indeterminate situation. It could be that you can't the number of equations, you have more unknowns than the number of equations. In that case, you cannot solve for the unknowns. Um, so there would be other ways outside of this course where you could solve those problems. You would have to know more about like the materials used, so it's a more advanced topic and the structure. Uh, okay. Sometimes the ordering too of how we're going to solve a problem may simplify it. Okay. If you only have one unknown horizontal force, two unknown vertical forces, it might be quicker just solve for the horizontal forces first, right, and then work from it that way. Okay. The only last point here is what I mentioned before that if the number's negative, then the force itself is just in the opposite direction, equal magnitude but the opposite direction of what you've originally assumed. Okay, so we'll look at a problem. Here's a problem here, and you'll notice that it has one of those two force members here, right? Connecting, there's a force acting here and another one acting here. So that would be equal and opposite. And in this case, what we're looking for is we want to know something about what's happening at A and what's happening at C. So we really don't necessarily need to draw like a free body diagram what's happening at D because that's kind of outside of the scope of what we need to solve for. Okay. So first thing is we can come up with a x and y axis, right? In our horizontal, vertical directions should work out pretty well here. And you could even make this like your maybe A is your origin, starting from there and going up from there. Okay. Um, so the next one, determine if there are any two force members. Well, yes, we see this one right here. Draw the complete full body diagram of the boom. And what you're going to notice that if like I said, if what you're going to have, if you're just looking at this beam right here, um, you're going to have this force acting down. From the beam's perspective, you have a force acting on it externally, and then you have another force right along this line, and you could probably tell from this that it's going to be a force that's equal and its opposite pushing back up at this point C. But you might not know the direction. But what we'll do is we'll draw a line of action, a force heading from basically from D to C, off in this direction of the beam of the connecting rod. And we also have reactions at point A. Well, this is a pin support, so it doesn't have a reactive moment. So we're going to have some reaction. Essentially, we could draw a reaction in the x direction and a reaction in the y direction. So right off the bat, if you look at it, you have an unknown force here, an unknown reaction in the x direction, and an unknown reaction in the y direction. So we have three unknowns, and with three unknowns, we have three equations. We have an x, y, forces in the x direction equal to 0, forces in the y direction equal to 0, and moments about any point have to be equal to 0. Okay, so if we use those three equations, we can actually go and solve it. Okay, so first part, coming up with your free body diagram, and there are the reactions. Now, as before, it's like, well, we draw these in the positive x, positive y direction. We could have drawn them the other way. What we'll find is that if the result is negative, what we know is that it's just in the opposite direction. Okay? All right. Okay. Okay. Now using the equilibrium equations. So first one is uh, we can start with just the moment and find FCD. Okay. Now, if we look at, and we're looking about the moment about A here. So if we do that, we only have this unknown force here, right? And in fact, if you think about it, you have um, an x component of this force and a y component of this force. The x component of this force, you can draw it straight through the line of action of the x component of the force goes straight through point A, so it doesn't develop any moment about point A. And A of x and A of y, those two are at point A, so they don't develop any any moment about point A. So now all you're going to have is you come up with a moment equation. You have the y component of this force times this distance, and that's going in a counterclockwise direction, so about point A. That would cause rotation around this way, which would be counterclockwise. And then you have this force at point B, which would be 1.5 plus 1.5, so 3 meters times 4 kilonewtons in the counterclockwise, in the clockwise direction, so that's negative. Okay, so if you perform the calculation, well, you set it all equal to 0, you solve it, and you come up with 11.31 kilonewtons, or 11.3 with 3 significant figures. Okay, so now we have this force FCD, and we still need to find these two reactions. Okay, all right. The next thing we could do is we can look at the A component, right? Well, we have, the X component. So we have a force acting in this direction, or reactive force, and we have the X component of FCDF acting in this direction also. So we write the equation, and those two have to be equal to 0. So if we sum those two, it's equal to 0. Both of them we're drawing and writing. Both of them we drew in the positive X direction. So A of X plus, we're putting in FCD, and here this is my X component of the force, FCD, and we're setting it equal to 0. So what we're going to be having, of course, bring this to the other side of the equation and solve for the reaction at A in the X direction, and that's going to be just negative 8 kilonewtons. Okay. Well, we do the same thing for the Y. We have a positive AY. We have the Y component here, and we have the this is all in the Y direction, so this is a negative going down. So we have one positive here, and a negative value here. So AY plus the Y component of the force, FCD, and we subtract out 4 kilonewtons going down. We solve for this, and we come up with minus 4 kilonewtons. Okay. And all we notice from this is that, what is this telling us? We don't necessarily have to go change the directions here. We don't want to change them because then it would just reverse these, right? But what it tells us that by saying AY is negative 8 kilonewtons and then looking at the free body diagram, what you can recognize that, oh, it's not really going up, it's going down, and AX is not really going to the right, it's going to the left. Okay? So it's important to keep that in mind, keep the free body diagram. Okay. Now, this is a little bit different than previously what we had. This is a distributed load acting on this beam. And the way it's drawn is it's a uniform distributed load. So the way to handle this is that basically you take this whole 5 kilonewtons per meter, multiply it times 4 meters, and now you're going to have 12 kilonewtons. And the place that it acts when you draw it like this, it's going to act when it's uniform like this. It's going to act in the center. So basically, we're going to replace this whole thing with 12 kilonewtons acting at the middle point. Okay. Now, looking at these, the support over here and the support over here, which really are that connect these beam to the outside world, or the external forces acting at these places. So we're going to have an external force acting here at the middle, 12 kilonewtons. Then this is a roller support. So there's no reaction, there's no reactive moment, and there's no reaction along this line here. So what we end up having is we have a reaction basically that's normal to the surface. That's up in this direction. Okay. And in our case, we could draw it toward the point A from here. And I mean, you could have drawn it the other way, but the end result, of course, would be that you would see it to be negative. This doesn't resist any motion up. Okay. And this one has 2. So there's 2 reactions here. So we're going to have 1 over here and 2 over here. And if we make this our X along the horizontal line here, that's normal to B, this line of action coming straight down. And then we have another one, or make one that's parallel to the surface, or right along this surface, that becomes our X. We could actually draw it right along and pass through B. That could be our, And then you have a y component, and the y component is basically just normal to that or perpendicular to a line made straight across here, okay, on the horizon or on the horizontal. Okay, so first thing is we establish that system. That's what I was talking about. Then we draw a free body diagram of the beam, and then the equations of equilibrium for the unknowns, solve for the unknowns. Okay, E of E. Okay. All right. So here's the free body diagram. Notice 1, 2. We have two reactions over here. We have only one acting at 30 degrees relative to the vertical, and we have this force acting over here. Okay. Now, looking at it, you can think about, you have different ways to go about solving this. What we could do a number of ways. We could start out, if you notice that this is acting at some distance. So if you come up with a moment equation, the moment equation is going to have two forces here, one acting the x direction, one acting in a y direction of force. And they're both acting at some distance from point B if we did the moment about point B. Um, so we would have two unknowns with that. We also have our force equation, so you could break this up into x and y components, and you could come up with a force equation for that. And then we have the y, which we don't know what this is. This is 12K going down, and then we have the components there. Okay. All right. So we're going to use all three equations. Okay. So the first one is the moment about point B. Now, one of the things you're going to notice here is that you have, like I said, you're going to have a component, and we need to pay attention to the distances, right? So if we were to come up with and draw a line like straight out here, what we would find is that, we know the length of this beam, but we need to find the component here we know the length from here to here. So to give you where this thing acts, the point at where this acts, we need to come up with the horizontal of this, which is just the cosine of 30 degrees times 3 meters. That will give us a line straight out to here. And then we can use that to actually, along with the y component of this thing acting straight up, and then we could come up with just the moment due to the y component. Okay, so there's the part that's acting straight up is this, the cosine of this. Okay, and then here we have this NA times the cosine of it. That gives us the vertical component of this force. And then here, 4 meters plus this, which is the length from here to here. Okay, so this gives you like the moment due to the y component of this thing, of this reaction. The next one is that we want to do the moment due to the x component. Okay, so if we draw a line, if we come up here and we find the x component, what we're going to find is just going to be the sine of 30 degrees times NA, which is this. And then the distance is just 3. It's this length from there to here. And that is just 3 times the sine of 30 degrees. Okay. This would actually cause clockwise rotation, so it's negative. The other one also causes clockwise rotation about here. So this one is also negative, right? And the last part we have here is this 12K Newton force is acting in the opposite direction. So this is actually in the would cause counterclockwise rotation about B, and that gives us, and then the distance it's acting is 2 meters, so that's the 12 times 2. Okay, so we can go ahead and work this out, and if we solve for it, we'll come up with 3.71 K newtons. All right, so that's the first one. We have this, and we have its direction. All right, the next thing we need to do is look at the forces in the summation of the forces in the x direction. So we're going to have the x component of this and bx in this acting off to the left, which is positive. Okay. Oh, sorry, not positive. It's acting to the left, it's negative. Okay. So this one is positive, this one is negative, because that's where we drew the, you could have drawn it in the other direction, it really doesn't matter. But the author chose to draw it off to the left. Okay. So this one becomes the 3.713, which is just essentially the what we had previously found, right here, the magnitude, times the sine of 30. So this is giving us our x component, which is essentially this side of it. Subtract it from bx, and you can use that to solve for bx. So bx is just going to be 1.86 k-newtons. And drawing them off to the left, um, which is, as long as you pay attention to this, this is the actual value, right? Whether or not you put an arrow here, if you have the free body diagram also provided, what it's just saying is that the direction you drew was correct if this is positive, okay? And by, same thing. Here now you're going to do the cosine of this, so which is pushing straight up. So that's along this side. So, um, or if you want to think about it along this side, it really doesn't make any difference in terms of how you calculate it. So it's pushing straight up. That's this component right here, minus 12, because that's acting down, and by is positive because it's going up. You go in here and solve for by, and you're going to come up with 8.78 k-newtons. Okay, so that's just gives you a basic, your basic approach to solving a problem like this. And it was the same thing. You know, this one was determinant. We could find the values because we had 3 unknown forces, and we had 3 equations to handle those. Okay, and that's good for now.